Welcome to another example of kind of a test. Well, this is more like a quiz. Now this one is on wave interactions. So let's dive in and let's try to see if we can solve the particular questions. As usual, I will put up a link. You can download the quiz for yourself. You can try it beforehand and then come back and then see the solutions. So let's give it a go. So there's quite a few multiple choice questions in here. And then I have added about 3 questions in terms of calculations, okay, and conceptual items. So in terms of calculations, I'm going to be rounding. We'll keep it to 3 significant digits if necessary. We'll keep things in SI units, right, unless otherwise stated. So, and we'll try not to round in intermediate steps. I don't think that we'll run into any issues with this material here. So here's question number 1 on multiple choice. And so wave interference refers to, well, so the transfer of energy between the crest and the trough. Well, no, okay. When 2 or more waves interact with each other, that is correct. Okay, so this one would be B. Now, the superposition of multiple waves. So certainly you do have superposition when wave interference happens, but that's not what wave interference actually is. It's not superposition. And then unwanted energy transfer within the wave. Well, it can be unwanted or wanted, but that is not an example of wave interference. So B stands. All right, so for number 2, let's take a look at that. So when 2 waves superimpose over each other and the amplitude of the result is reduced, then what this is called? Well, so if you have a reduction and waves are being superimposed over each other, so here is, okay, so here, notice it says reduced. So that's going to be destructive interference, right? Okay, so within here, so, okay, destructive interference, so that would be D right there. The other ones are not true. Constructive interference means that the amplitude would have been increasing. Number 3, let's dive into this one. When a pulse wave with negative amplitude travels from a less dense to a more dense material, then the reflected wave will, all right, okay, so this is kind of like, you can think about, so I'm going to draw. So let's say it says less dense and then it becomes, more dense, okay? So I'm going to really make the more dense really more dense. All right, so here, so it's less dense to a more dense material. So there you go. So this is what we have. And, we have some kind of a wave. Now it says it's negative. So within here, so let's draw that in. Okay, so let's say it is negative like this, and it's moving along in this direction, right? So what will happen? Well, when you go from less to heavier dense, it basically acts the same way as if it would hit a fixed, right? So this, if it was, okay, if this is a fixed end, okay, almost you can assume, right? So you have a fixed end or a free end. So in a free end, it will come back. So the reflection will come back in exactly the same way. But in a fixed end, it actually goes back, okay, and then flips over. So it's kind of the reflection, okay, back in. So that means we want to know what happens to the reflected wave. Well, the reflected wave is going to come back, and it's going to come back. Now it's going to come back in this direction right here. It is going to be less because some of the energy is going to transfer, right? So it's going to try to transfer in this particular direction. So that's what you would have in there. So some of that wave will happen. Okay, however, okay, it's going to be less. So have a negative higher amplitude, have a negative lower amplitude, have a positive higher amplitude. Well, it won't be higher, it's going to be lower. So positive. So there we go. So we can highlight, so it's going to be a positive but lower amplitude. So this is what's going to happen in here. So it is going to reflect back in. It's not going to come back the same way. If it was coming back the same way, it would have gone from you know, for example, a more dense, okay, to a less dense, which then would be acting more like a free end. Number 4, so standing waves. All right, so standing waves can be captured for any frequency. No, that is not true. Okay, so standing waves do occur, but they happen for particular frequencies, you know, for a given length, whatever material that you're working with. And then it's just replications of those, right? So we have various kind of harmonics that we call them, which are going through. So B can be set for only lower frequencies. No, it can certainly have higher frequencies as well. Are formed by the superposition of incoming waves. No, it's not just the incoming waves. It would be also the reflective waves as well. So that one won't work. D are only for fixed end media. That's also not true. So here we actually do not have, okay, an answer. So it would be none of the above in this particular situation. Okay, so not A, not B, not C, not D. Okay, so let's continue. Number 5, assume that 2 waves interfere with each other and the frequencies are, so here they give us 2 frequencies. The beat frequency will always, well, so recall, so that means the beat frequency was equal to the magnitude of the difference between the 2. Now, if this one is bigger than this one, so this is actually going to be positive, right? So that's what you have, but it's going to be less, okay, than the bigger one that we have. So what does it say here? B, the beat frequency be larger than the faster? No, so that's not true. Be equal to the faster wave frequency. Okay, so within here, so no, not necessarily, you know, be smaller than the faster wave frequency. So here, I guess faster and slower, so we have to kind of be careful. So I'm going to make an assumption. So faster just means that the frequency has actually a higher frequency, right? And then the slower just referring to the lower frequency. So be smaller than the faster wave frequency. So that's actually true. So it will be smaller because notice that you're subtracting the F2. Be equal to the, no. Okay, so not necessarily, so that's not true. So C will hold. All right, question 6, damping. So damping basically is a reduction, right? Okay, so let's take a look. So it is a reduction of amplitude of the wave transfer out of energy. Okay, well, there you go. So that's right away, that's easy. Okay, we have it. B also says reduction of amplitude of the wave transfer in. No, we're not receiving energy, we're actually transferring out. So it's kind of like a thinking of loss of energy, right? So damping is basically it's being damped down in terms of its amplitudes. Question 7, the frequency that allows the material to vibrate most easily is known as, so the frequency, so that's called resonant frequency. So this one again is another easy one. So that is about it. The other ones are just hoax. Okay, damping frequencies, wave frequencies, Doppler frequency, resonance. Well, so resonance certainly is a part of this, but resonance is not a frequency. So it will be resonant frequency that we want. 8, I guess this is the last multiple choice. When an object giving off a sound moves away from an observer, then, all right, so I have to, we kind of have to draw this out. So let's say, we have an observer right here, and an object giving off a sound is moving away from right here. So it's moving away from the object. Then the observed frequency is actually going to be smaller, right? Observed frequency disappears. No, not necessarily. Doesn't this just disappear? Observed frequency increases in pitch. No, it does not. It decreases in pitch. All right, so that will be C. Okay, so that is due to the Doppler effect, right? So if it was approaching the observer, it would actually be increased in pitch. Moving away, it would be decreased in pitch. Okay, so that is it for multiple choice. Here's our next example. So this one we have to do a little bit of work. So use superposition to construct the resulting wave that is frozen in time in the below diagram. So you have kind of two waves in here. They're kind of weird, or at least two impulses that are passing each other by, and they're frozen in time. So how would you approach this? So I'm actually going to draw right on top of it because it's the easiest thing to do. So what I'm going to do is first, okay, so notice the first interference of first interaction is kind of between here and here. And all I do is at those points, right, I will just add up the amplitude and then see what happens. So it's really 2 plus the 1, so that's going to result, okay, in this being all the way over here. So that's the first one. Nothing happens on this end, right? So this thing just stays the same. Okay, so that is identical. Now I can move over. Okay, so here, okay, this one ends over here, and then this one is over here. So that's going to be 1.5 plus 2. That's 3.5. So that's going to jump this one upwards, okay, in this direction, and it's kind of going to do something like this as you're going through. Then we have, I guess, okay, so here we have to be careful. Okay, so as you're going through, so it's going to be between this one and this one. So 2.5 right there. Okay, so as you're going through, so that's 2. Okay, and then a half that we have. So that is going to bring us back down. So that's going to be somewhere over here. Okay, so that's the addition, okay, of those two. Now also take a look here. So although these two, okay, so when you're adding it up, it's going to kind of result in the higher up, but also, this wave then drops down, right? So it drops down to here. So we have to also capture these two together. So that's going to be 2.5. Okay, so therefore it kind of will do something like this, where it's going to drop down right here, and then this is going to be just carrying through. Okay, so that's how it's going to continue on. Okay, so that's what we have. Now, once again, you have the same problem over here. This one drops down, right? And this one continues on in this way. So that's going to be 1.5. So it's going to drop down to 1.5, because it's 1 plus a half. So it's going to drop down here. So this continues on downwards, okay, like this. Then you can continue it further. So that's going to be this one and this one, okay, as you're going through. So it's going to be another 1.5. So that continues, okay, in this direction. So that still stays, okay, kind of like that you have. And then afterwards, so then it starts to drop down. So that's going to go 1.5. So that's, these two together, okay, so this one and the blue one, so that's going to go down to here. This is a really nice test of understanding superposition and then just adding things up. So that looks like this, right, as it carries through, and then so one of them just completely, drops down. So notice again, so here you have to be careful. So this one, the blue one, is gone, right? And then afterwards you only have this one. So that's going to go down, and then it's actually going to follow this all the way through. And then on the left-hand side, so this would have been following this, and then this would have been just jumping up, okay, upwards like that. So that's what would have happened. All right, so, I can, just so that you have it, okay, I'm going to duplicate this, bring it back down. So this is how it would look like, okay, according to that. And let me get rid of all of these little points, okay, so within here. And so that's, actually, let me leave those ones. Okay, so that's how it would look like. That's the superposition, okay, of those two kind of impulsive waves passing each other by. Now, if they go left or right, doesn't really matter. This is frozen in time. This is the best we can do for this. And then, you can certainly label all of the amplitudes. So the peak is 3.5, and then you can label the rest if necessary. So that is it, all right, for this example. It's a nice one, okay, that tests you an understanding of superposition. Here's the next example. I've actually added, so if you've downloaded this handout, this wouldn't have been there. I've added it in. right here because I just want to remind you, because this example has to do with standing waves. So in a laboratory, you're observing a set of standing waves, right? Now, if you're talking about standing waves, so you have either, two fixed ends, two free ends, or a fixed end and a free end. Now, in this case, we have a fixed end, and then we have one free end right here. So that's the first thing, and that's why I kind of took these two things out. So recall this right here between the length, okay, and so n stands for the harmonic that you're referring to. This is the wavelength, right? This belongs to either two fixed ends or two free ends. In our situation, we're dealing with this right there. When you have a fixed end or a free end. Now, it doesn't matter if the fixed end is on the left or on the right, but one of them is fixed and one of them is not. So here it says, the goal is to create a standing wave under the fifth harmonic. So notice, that's what we want. The length of the device used is 2.5 meters. Okay, so let me write this down. So n, so that equals 5, which means that we would have had L5 is equal to, right? So 2 multiplied by 5 minus 1 divided by 4 times the wavelength. So that's 10 minus 1, which is 9 over 4 right there. Or simply, this is going to be 2 1/4 of a wavelength, which is equal to the entire length of the string. All right. Now, the length of the string, so here for us, is 2.5 meters. If the frequency is to be set at 320 hertz, frequency is 320 hertz, then what would be the expected speed? All right. Okay, so we want to know what the speed would be. Now, please recall, so this kind of goes back. So speed is equal to, length. So the wavelength times the frequency, or frequency times the wavelength. So this is the universal speed equation of the wave. Now we have the frequency. We can actually definitely find out what the wavelength is because we can substitute this back into here, right? So we're going to be able to find that out. So for instance, this is going to be 2.5 meters is equal to, I'm going to keep it as the fraction, so I can find out what the wavelength is there. So here's our calculator. So we have 2.5 multiplied by 4, that's 10, and then divided by 9. So I'm going to leave it, so just keep it as 10 over 9 equals to the wavelength. That's going to be in meters right there. And then we can find out what the actual speed would be. So V is equal to, so it's going to be 10 over 9 multiplied by the frequency, which is 320 hertz, equals, so since I already have this on the calculator, multiplied by 320. So this is 355.5, etc. meters per second. So I guess the three significant figures, this is 356 meters per second. That would have solved the problem. Now they do ask us, so notice sketch the appearance of this standing wave. So that's actually a pretty good exercise. When you have this, I can put up a link to the standing waves, for yourself. But notice that here, so the entire length is equivalent to 2 1/4 of a wavelength, right? So if this is one free end, one fixed end, so within here, here it says, okay, so fixed end. So I'm going to start from a fixed end right there. And now we're going to have to try to draw, right? So this is going to look, so it's going to go up, it's going to go down. So that would have been just one of these, right? Remember that a wavelength is equivalent to the total distance of the period. So that would have been 1. So let me now take this. Actually, I'll shift it over. Duplicate it. Again, this would have been 2, right? So it kind of looks like this. And again, I'm going to, shift it over, right there. And maybe let me change the style. So it pops out. So that's 2 of those wavelengths. So when you're drawing this out, it's actually pretty neat. So that's the 2, and I still need a quarter. Now remember, a quarter, so it's going to be a quarter of the entire 1. So this one is fixed, right? So a quarter is going to be just, literally a quarter of this. Okay, so this would have been a quarter, this would have been a half, this would have been 3/4, right? And then the entire wavelength. So really, we're just continuing on to the peak, right? And this one is the open, okay, one. So as you're going along, kind of looks like this. I know I'm just sketching this out, but that's all they asked just for a sketch. So this would have given us 2 1/4, and that's how it would look like. So this is really nice because, it makes you understand, all right, how many wavelengths are there? It's 2 1/4 of a wavelength, which is the entire length of whatever string you're dealing with in here. And that will be it for this example. Here's our last example. So within here, so another calculation. So on a cold winter day, so -15, a police vehicle. I put a little footnote. I actually inputted in. I wasn't sure actually myself, like what are the siren frequencies of these vehicles? And, I put this actually into Open AI's ChatGPT, and I asked and it answered. You can see there at the bottom. Okay, typically it's between 500 and 1500. You can, of course, also put it up in your search engine. Not that it matters, right? But I wanted to make it semi-realistic in here. So I put that the siren is 750 hertz in here, okay, for this vehicle that we have. And, so we're on a cold winter day here. We're moving east, all right, and we're sounding a siren, which is the 750. And now this is what we want to be able to do. So if you are on your bicycle, moving in the west direction, so actually in the opposite direction, at 24 kilometers an hour, then what would be the observed pitch frequency from the siren? All right, so we're going to need a couple of things. And again, so if you're downloading this for yourself, you would not see, I inputted these 2 formulas, okay? So within here, this one is related to the speed of sound depending on temperature. So if you recall, so there are actually, I presented 2 formulas. Most of the time, you might just be presented with this linear formula right here, which is good enough. I'll do calculations for both to find out what the speed is. They should be very close to each other. And I can put up a link up above there if you want to go back into learning about the speed of sound dependent on temperature. All right, so I needed this because I'm going to need to know what the speed of sound is. And I need this, so recall this is the Doppler effect, right? So this is the frequency that you observe coming in from a source. So in this case, it's from the sirens of the police vehicle. And then, here's the sound of the speed. So we're going to get that there. And then we have these 2. Now, the only thing we have to be careful about is, are these pluses or are these minuses, right? And that goes back to understanding, all right, so what happens in the Doppler effect, right? So what is happening in here? So let's write down all of the given pieces of information. So the temperature, so -15 degrees Celsius. Here the temperature indeed is in degrees Celsius. All right, so we have that set. We also have the vehicle. So that would have been the speed of the source. I'm going to just put S for source, okay, within here. Maybe I should write source so that's not, so that we don't run into problems of VS meaning V sound. All right, so I'll keep it as source. So that's going to be 85 kilometers. Okay, and this is east, right there. Now, our bicycle, so this is the speed of the observer. So that's going to be 24 kilometers, okay, per hour, but it's west. So they're going in the opposite directions, okay, right there. And so what else do we have? We have the siren, so that is the frequency of the source, which is equal to 750 hertz. All right, and let's now try to break this down. All right, so One of the things, okay, in here is, our speed is going to be in meters per second for the sound. So we need to have those consistent. So you either have to change everything to kilometers per hour or to meters per second. So that's up to you, okay, how you do that. Since I already have these two in kilometers per hour, I'll find out my speed and then I'll just change it to kilometers per hour, because when I substitute it into here, the kilometers per hour and kilometers per hour, so in the numerator and denominator, will cancel, right? Therefore, just giving us a ratio, really just a scaling, okay, between the two frequencies. So it won't matter as long as you're consistent, all right? Okay, so the first thing that I'll do is let's take our equations. So these two, okay, equations, I'm going to put them in here and I'm going to do a quick calculation. So let me just substitute. I'm going to see both of them. So I'll do that in quick fashion and let you know what the speed of sound is. All right, so here are the calculations. Now notice I have changed it back to kilometers per hour. Changed it back to kilometers per hour, so you're going to have to change units there. Very quick thing is just to multiply by 3.6. Right, so if you're going from meters per second to kilometers per hour, so you can do that, okay, and you'll get that. Now notice both equations basically give us the same thing, so 1159.8, right, and if you round these, they're both 1160, okay, so I'll just use 1160, okay, in terms of my speed of sound. So let V, in terms of the sound, be equal to, this is going to be 60 kilometers per hour. All right, so although it says, don't round in intermediate steps, in this case I have 4 significant figures, okay, so within here, so that's already pretty good for this example in terms of scaling. And now, notice that I am keeping all of these in kilometers per hour. So if you want, you can certainly change them all to meters per second, and you'll get exactly the same answers. The trouble is actually when you're now going to be substituting into these. So what should we do? Is it going to be a plus or is it going to be a minus? So I do these kind of one at a time. So I know that, for instance, when your source is moving away from you, okay, that will decrease the pitch of the observed frequency. So decrease. And the source, notice, is in the denominator. So in order to decrease that ratio overall, then what that would mean is that this right here, we would have to add, right? So this is going to be a plus because it's going to make the denominator bigger, therefore the fraction smaller, and hence, the observed frequency is going to be smaller. So that's for the source, right? So this is what we're going to have right there. Now for the observer, so now you can move up to the numerator. Well, the numerator that you have for the observer, so again now, in this case, the observer is moving away from the source. They're both moving away from each other. So again, it's going to make it even smaller. So in that case, since it's in the numerator, this is going to have to be a subtraction because it's going to make the numerator smaller, and therefore the overall fraction smaller as well. So with that being said, then we have our frequency that the observer has is, okay, so the sound, so I'm going to put it 1160 minus the observer, which is 24, divided by 1160, and then plus the source, which is 85 kilometers an hour. This is all in kilometers per hour, and then we have 750, okay, which is our source frequency. So now we can just pop it into the calculator and find out what the answer is. And our answer, so there you have it, and fast forward to 3 significant figures, is going to be this. So notice it is indeed lower, right? So it lowers it down to that. So I encourage you, to try this out. This was actually a fun example. It forces you back into the Doppler effect, understanding the equation, and it also brings you back to understanding how to find out what the speeds, right, of sound is dependent on temperature. Now, because when it gets colder, the speed of the actual sound decreases, right? And you saw that. So it's 322 meters per second instead of the typical around 331, okay, in more or less kind of neutral temperatures. All right, so that is it. So I hope that you found this quiz helpful in terms of your study habits. Okay, thanks for watching. We'll see you in future videos. Bye, everybody.